In this video from the Signals and Systems series, we're going to focus on signal energy and power. So first thing is power. Typically, we represent power as being proportional to either V squared or I squared. For example, if you're looking at a resistor by itself, you remember that is V squared over R. And if you're looking from a current point of view, I squared over R. I squared R. So in general, what we do when we are talking about power, we take power at a given point in time to be the magnitude of whatever signal we have squared. And that allows us to use x of t as a placeholder for v of t or I of t, depending on what we are trying to do. So in general, that's what we look at. Now, you recall that if you're looking for energy, let's say somebody's asking us for a total energy let's say between an intervals of t being less than t1 to greater than t2 greater than or equal to t2. And you recall that energy is the area under the power curve. So basically it's the sum of all the power over this period of time. So the easiest way, or the only way we know how to do that, is energy is going to be the integral of from t1 to t2 of p of t dt, or we can go directly to the signal and say that's basically going to be the magnitude of x of t squared. Okay, so these are kind of different ways of writing power and energy. So what we're going to do, and so far first we're going to start with continuous times, as you see, and then when we finish with continuous time, we'll come back and do the same thing for discrete. And for most part, just the independent variables will change. Okay, so if we've got a continuous time signal, such as x of t, and we are asked to find a total energy for the interval, let's say for the interval t1 less than or equal to t less than or equal to t2, we already figured that out. That's relatively simple. We say, okay, that's great. So that would be, energy would be equal to integral of t1 to t2, and then magnitude of our signal, x of t squared dt. Great. We can take this one step further. I'll come back in a minute and do that. But for the time being, that's energy. Now, how about someone says, what is the average power during this period of t1 to t2? So energy was the sum of all the power during this period. So if I divide it by the interval, I have got the average power. So if they're looking for average power, I simply say P, capital P, average power is equal to 1 over T2 minus T1 integral of T1 to T2 of x of t magnitude squared dt. Okay. So that's great. That's great. The one thing we could extend it, this is fine for a defined version, but once in a while we would have this situation where someone will ask us to go a little further and asks us to say, okay, what is the average power from minus infinity to infinity? Okay. So if someone is asking for a energy for t when it goes from minus infinity to plus infinity, you say, okay, well, I can't quite put the minus and infinity and plus infinity there. I suppose I could, so that's no harm done. So, but we usually in mathematics we write E energy over a total period. They usually write it like this: goes from minus infinity to infinity, is equal to limit of t going to infinity, and then integral of minus t to t of x of t, magnitude of x of t squared dt. That's not too bad, and and then we can kind of we can almost get rid of the limit in this case and write it as integral of minus infinity to infinity of magnitude of x of t squared dt. Great. Now, how about if they come back and want us to find average power when t is going from minus infinity to infinity? And if that's the case, we're going to look over here to this equation and say, boy, infinity plus infinity, that gets a little bit tricky. So let's go ahead and write it this way. So, okay, my t1 is minus infinity, my t is infinite. So my power for infinite, it's going to be equal to limit again, limit of t as t goes to infinite, right? And then now we're going to divide it by the interval. This time the interval used to be t2 minus t1. In this case, it's going to be t minus t, and the integral is going to go from minus t to t x of t magnitude squared dt. So if we do a little bit of cleanup on this again, basically we can rewrite this one as limit of t going to infinite. Unfortunately, we can't get rid of the limit like we did for the energy because we've got 1 over 2t, which is infinite. So we need to keep it so in case we want to calculate it, we can decide what actually is the infinite that we want to use in our approximation. So minus t here, and then magnitude of x of t squared. Okay. So that's as far as that's concerned. Now we can almost do the same thing for discrete. So when we have a discrete time signal is x of n, and remember the only difference, t is time, n is number of samples, which sample number you're looking at. Okay, so if you look at this one, we could also write the total energy for the period. In this case, n could be less than or equal to from n1 to n2, and the process is similar. So your energy would be basically, instead of being t1 to t2, and oh, by the way, is it the summation? No longer a summation, because n is integer. We don't know what's between n equal 1 and n equal 2. So this will turn into not an integral, its counterpart, which is a summation, where n goes from n1 to n2, and again the power still for n is calculated as magnitude of x of t squared. And we could do the same thing for average power in the same interval, and that would be basically taking the energy, dividing it by the interval. And in this particular case, as you think about it, you have to add a n1, you have to add a 1 to the thing. So n2 minus n1 plus 1 is the interval that you're talking about. The rest would be summation of n equal to n1 to n2, and then there you go. Okay, now just oops, both of these I should go back and correct them. And this is going to be something you will get trapped in as well. When you're in discrete, this is x of n. When you're in discrete, this is x of n. So I'm glad I made this mistake so I can come back and emphasize that when you're in discrete, you have to use this form. And if you use x of t, that is actually wrong. Okay. Now we can continue on much like we did before and say what happens if we have, again, we want the total energy, and we want the total energy to be from minus infinity less than or equal to n to less than or equal to infinity. Again, much like we did before, that's pretty much a straightforward conversation. Instead of having an integral, since this is discrete, and we'll have e of infinite equal to summation from minus infinity to infinity of x of n. This time I'll remember to do x of n squared. Okay, and then continuing on this one, then we're going to have average power from minus infinity to infinity, same interval as we had up there. We have to do the same thing, the limit business and all that. And the only difference is we're going to have a +1 attached to it, just because of the way the discrete intervals are calculated. You have to add a 1, otherwise you're missing the point. And so p infinite in this case is basically going to be limit of n going to infinite and 1 over 2n plus 1 summation of n going from minus n to n x of squared. Okay. Now, based on this process, we classify our signals based on what their infinite, their total power and average power is from minus infinity to infinity. We classify them, and the classification is more or less the same for both of those things, where we're going to end up with 3 classifications. There's another classification which is kind of useless when power is 0 and energy is 0, because there's nothing. But in typical cases, we have one class is where energy in the infinite is less than infinite, which means if that is the classification, then by definition power infinite has to be 0, because if anything other than 0, when you sum it over an infinite period, it's going to be 0. Another class of signals are signals that have their average power is larger than 0. If the average power is larger than 0 over an infinite period, then by definition the energy is equal to infinite. Kind of common sense. And then the last one, which is kind of, again, is not really that relevant, but if p of infinite, if the average power is equal to infinite, guess what? Energy is also equal to infinite. Most of our systems, most of our real system that we deal with fall in this category, okay? Because if we have power, and so our systems have a power at a given point in time, but then they stop having power at a certain time. So when you average it over an infinite, they go to 0. So most real systems in the world, I think, got classified as that class of signals. That brings us to the end of our conversations about power and energy for signals.